So in this chapter, we introduced this chapter last time. It was focuses on energy, mechanical energy equation, conservation of energy. It's described as the Bernoulli equation, right? We started with a review of mass balance, volumetric flow rate, mass flow rate, the average area or the cross-sectional area and the average flow across that area. Then we went into the Bernoulli equation with conservation of mechanical energy made up of three components: the flow energy, the kinetic energy, and potential energy. We also covered the Torricelli's equation. Now we'll just apply Bernoulli's equation to a bunch of application problems and then modify it so that we can account for head gains or head losses, and so that mechanical energy can be put into the system via pump or a turbine, or taken out via friction or valve or other restriction, or even a turbine to extract mechanical energy out of the flowing fluid. This equation, or this type of summary of the material that we covered last time, here's one way to write Bernoulli's equation. Here's another way to write the same equation. Here's another way to write it. There's three ways that I would ask that you become very familiar with. Why? Because they're helpful. So one, you could see from this term that it's written in terms of pressure. All of these terms have units of pressure. Pressure is kilopascal, but it's also can be viewed as kilojoules, some amount of energy per cubic meter, energy per unit volume. Pressure has the same units when you're thinking about the Bernoulli equation, and it's described in terms of pressure. It's a conservation of mechanical energy, and that energy in each of those terms can be described as energy per unit volume. Okay, let's take a look at the next equation. Each term, you can see it by this, is V squared over 2. That's specific kinetic energy. Energy per unit mass. So it's kilojoules per kilogram, each one of those terms. Sometimes they'll talk about energy head, or sometimes they'll say that's head, but really head is a term reserved more for energy per unit weight, which has the same units as elevation or meters. And somebody says meters is interpreted as energy per unit weight. Yes, it is. In the Bernoulli equation, each one of these terms is in units of meter SI, and it's interpreted as energy per unit weight. Okay, so each one of these three terms represents flow energy. Each one of these three terms represents what type of mechanical energy? Kinetic energy. And each one of these three terms represent what? Potential energy. A lot of times I may emphasize gravitational potential energy, right? And for flow along a streamline, steady state, it's incompressible, it's inviscid flow or negligible frictional effects, no heat transfer, no work transfer. It's just conserved mechanical energy. The energy of that pack of fluid flowing through that system can change between the potential energy, kinetic, and flow energy, but the sum is conserved. That's what they're saying. The sum is equal to a constant. All that makes sense? Good. Now you're ready to launch in and solve a lot of problems. Why not solve a problem right away? A pump increases the pressure of water from 100 kilopascal to 900 kilopascal. So there's a change in the pressure of 800 kilopascal of the water. The mechanical energy increase of the water in units of kilojoules per kilogram is, and then what is it? 0.8 kilojoules per kilogram, blah, blah, blah. What is the answer? So we'll go ahead and start it. And I'll go ahead and give you some time, extra time. All right. So there's a couple of ways to solve this problem. Let me try this. I'm really interested in energy. I'm interested in mechanical energy. And we talk about how you can describe the energy of the fluid, like water, per unit weight, the energy per unit mass, and the energy per unit volume. Okay. That would be like talking about pressure. This one is a specific head. Maybe I'll use it as cap H as the energy per unit mass head. And this one is lowercase h for the head that most people would say the head of the fluid flow is so many meters of head. Okay. Well, we want to be able to go back and forth between these systems. What we're saying is the change in the mechanical energy is represented by, in this problem, 800 kilopascal increase. True? Well, what was the increase in the head in units of kilojoules per kilogram? And what was the increase in the head in units of meters? You could do the same thing, but okay, we only really need to go from here to here. How do you go from energy per unit volume to energy per unit mass? So if you take you do it this way, energy per unit volume, and you multiply by mass per unit volume, so you would have the change in the pressure times the density. Is that true? Is that equal to the head, which is the energy per unit mass? Okay, so we have 800 kilopascal divided by 1,000 kilograms per meter cubed. At this point, a unit conversion factor of a pascal is a Newton per meter squared. Or you can skip a lot of those. What's a kilopascal times a meter cubed in terms of units? A kilopascal times a meter cubed. Kilojoule. It's a kilojoule. So, I mean, you can work through, let me finish this since I started this. You cancel the pascals. Then what's a Newton? A Newton is a kilogram meter per second squared. But hold it, I don't want to do, I want to do a joule is a Newton meter. True? So the Newtons go, and what we have is the kilojoule. The meter cubes all cancel, and there you go. So you'll be left with what we have as a kilojoule per kilogram. And so the answer was A. Congratulations, 50%. Let's talk about a nozzle. We've studied nozzles in Thermo 1, etc. But here we have, it's a section of flow where it contracts and goes from a larger cross-sectional area at state 1 to a smaller cross-sectional area at state 2. Okay? Much smaller as I've shown it. And so if we apply Bernoulli's equation, you can apply either of those three forms. I'll apply the pressure form, so P1 plus 1/2 rho V1 squared plus rho G Z1 for the fluid particle going from state 1 to state 2 equal to the pressure at 2 plus 1/2 rho V2 squared plus rho G Z2. And what we notice is we're not interested in a change in elevation for a nozzle, but we find that there is a difference in the pressure. So if I look at this equation, what about the speed at 2? Do you think it's kind of went up? Yes. Yeah. Compared to the speed and the kinetic energy at 1, it went up. So what about the pressure at 2? Do you think it's going to go down such that the sum of P plus 1/2 rho V2 squared is the same as P1 plus 1/2 rho V1 squared. So you think that P2 is less than P1. It went down compared to the inlet pressure. And that the kinetic energy, let me write it like this, 1/2 rho V2 squared is greater than 1/2 rho V1 squared. Do both of those statements look reasonable? Yes. Sure. Now, this equation we've applied is for something like water flow. It's incompressible. Or if you have air, as long as you're not subjecting it to significant pressure changes and temperature changes, you can often treat air as incompressible as well. I know you start to really increase the pressure, change the temperature, it's not incompressible. The density is not, constant. It starts to change, but you can treat it as being under these conditions as if the density doesn't change, quote unquote, it's incompressible, even for air. But let's take a look at if I had the area, cross-sectional area at 1, and I had the area at 2, is there a relationship about the mass flow rate? Would the mass flow rate at 1 equal to the mass flow rate crossing at 2? Yes. Steady state? Sure. Would this be the density at 1, the area at 1, the speed at 1, the density at 2, the area at 2, the speed at 2? This equation is from a mass balance. This equation, Bernoulli's equation, is from an energy balance, more specifically mechanical energy balance. Mechanical energy is conserved. Okay? So one concept, the mass, we can combine these now. Let's go ahead and cancel off the densities because we're implicit in Bernoulli's and it's incompressible. And so what we have is that the velocity at 1 is equal, let's do it. The velocity at 2 is equal to the velocity, let's leave it 1. It's 2 times area 2 divided by area 1. Okay? So what we can do is include that over here, and you can write an equation that let me see if I can get it all down without too much algebra. 1/2 rho, let's put V1 squared times, and for V2, I wanted it the other way around. Here, I can write it as either V2 is equal to V1 times A1 over A2. Okay, that's great. So we'll substitute that right in here, and then we'll bring it to the other side, and you'll have 1 minus A1 over A2 squared. And let me do this. I'm going to switch it around. P1 minus P2. Then this gets to be A1 over A2 squared minus 1. There's my preferred form. Okay? That's my preferred form. Why? Because what about this P1 compared to the P2? Is this a positive entity? P1 minus P2, is that positive on the left-hand side? Yeah. And then what about over here? I have A1 over A2. Which one is larger? A1 is larger. So this whole thing right here is positive. And then I have a positive V1 squared. So everything, I don't have a negative sign that I have to work through in my mind. It's all positive. Okay. What Bernoulli's equation and the conservation of mass allows you to do is it allows you to predict what is V1 as a function of 2 pressure measurements. Let's put a pressure gauge right there and measure P1. Let's put a pressure gauge right there and measure P2. If I could just measure the 2 pressures and know the diameters, I know the inlet speed 1, V1. Check that out. So V1 is going to be 2 P1 minus P2 divided by rho A1 over A2 squared minus 1 square root. Just think about that for a minute. I can just make pressure measurements, measure the diameters so I get the areas, and I can get the velocity V1 on the inlet. You can then do this. You can then multiply by A1, V1 by A1, and what do you get? The volumetric flow rate. So you can use this nozzle as a measure of volumetric flow rate. Now, what happens after this? Well, it could issue out into the atmosphere, or a lot of times, if you're interested, this is called the Venturi effect. If you take that nozzle, neck it down, and then bring it back out, like that. Okay? What do we have? If you put pressure taps on this, and a pressure tap right there, and let's bring it out to the same diameter as what it started out as, okay? So this is the same diameter. Let's say D1. Let's call this one state 2, so diameter 2. And this is the exit, state 3, diameter 3. And if diameter 3 is the same as diameter 1, and you put a pressure gauge right there, and if you had inviscid flow, no friction, what do you think the pressure at 3 is compared to the pressure at 1? They're the same. But what about the pressure at 2? Lower or higher? It's lower. It's lower. The speed went up. So the fluid, if I wanted to show a little vector for V1 for the speed, if I went right here, I'd say, whoo, it's really long vector, high speed in the Venturi, in the throat of the Venturi, and then back down to the same speed. V3 is equal to V1, right? Good. So you can make a Venturi flow meter. What you would want to do is neck it down, get the pressure taps, get the 2 pressure measurements, and then because you're having a flow meter embedded in a pipe, bring it back up to the same diameter and let it continue. So this right here would be our section for the flow meter. Right? Same inlet, same outlet, same speed in, out. It's going to have, if you have full pressure recovery, it'd have the same pressure on the outlet. But this is, we don't have any frictionless fluids. All of our fluids are going to have some frictional losses. But it gives you an estimate of the volumetric flow rate. And we just worked out that equation, did we not? What was that equation for the volumetric flow rate? Well, we had the equation for the velocity, 2 times P1 minus P2, divided by rho, and then you had the area 1 over area 2 squared minus 1, square root. And then if you wanted to get the volumetric flow rate, you just A1 V1. And if you wanted the mass flow rate, density times AV, A1 V1. So you have a way of having a flow meter. You can measure the flow rate just by measuring pressures. Just by measuring pressures. Somebody may have also heard of Venturi in some other applications. Well, here's an application. Let's see if you can solve this problem. I'll give you 2 minutes, right? So air is flowing through a Venturi flow meter. The inlet diameter is 6 centimeters. The throat is 3 centimeters. The pressure at the inlet, 210 kilopascal. It's 160 kilopascal at the throat. And the air density is 1.2 kilograms per second. What is the flow rate of the air in those units, meters cubed per second? So the delta P is 50 kilopascal. And we'll give you enough time to solve this problem. You'll need a calculator. Area squared, diameter to the 4th. Area is pi d squared over 4. The ratio of area squared is the ratio of diameters to the 4th, right? So how many people got V1 to be around 74.5 meters per second? And then you multiply by the area 1 pi d1 squared over 4 times V1, and you pick up a volumetric flow rate 0.2107 meters cubed per second. A distribution. Maybe these quantitative are not so easy to do on the screen, huh? You just had to use the equation, but I know you're working with notes. Scribbling it down.
I got my formula perfect and I'm still getting it wrong number 3 times in a row.
3 times? Okay. Let me also talk about how the Venturi is not just a flow meter. It's used for a flow meter, but it's also very practical. Let's say I have a fluid in a duct system, but it's neck down, or pipe system, it's neck down, and then it expands back out, something like this, okay? And maybe I have the pressure at 1 back here, it's pretty high, P1, and maybe this goes out to a pressure right here of 0 it's atmospheric pressure, so it's 0 gauge pressure, okay? Well, right here, what do we have is we have a throat. So what is the pressure right here in the throat, the smallest diameter, before you open it up some? Well, isn't that going to be a low pressure? Okay. So tell me a little bit about the pressure between, let's say, state 3 and the pressure at 2. And forget about 1 for a minute. Just compare 2 and 3. If 3 is atmospheric pressure, what about the pressure at 2? 2 is the, okay, clicker question. Is the pressure at 2 greater than, equal to, or less than the pressure at 3? Answer A, B, or C. Is the pressure at 2 greater than pressure at 3, equal to the pressure at 3, or less than the pressure at 3? Well, before I show the results on that one, answer this question. What about the speed at 3 and the speed at 2? Which one's greater? 2 is faster. Let's draw it as a larger arrow, longer arrow. So it's slowed down, true? What about the kinetic energy of the flow at 2 versus the kinetic energy of the flow at 3? 2 is, so it's greater, right? But we know that the sum of the flow energy and the kinetic energy is a constant. True? That's Bernoulli's equation, neglecting potential energy. There's no change in elevation. So what is this flow energy? If you want, you write it as P. The kinetic energy is 1/2 rho V squared. The sum of those is the same. So as I move from 2 to 3, my kinetic energy is going down. My flow energy has to go up. So the pressure at 3 is greater. 83% correct. Got it? It's C. C. The pressure at 3 is greater than the pressure at 2. Pressure at 2 is the lowest pressure. Okay, let's say pressure at 3 is atmospheric pressure. Reasonable? Now, tell me, what about pressure at 2? It's below atmospheric pressure. You have a slight vacuum. You can use this, and a lot of tools and devices use this to great effect. And so what they do is they put a little tube down from the throat that connects into the throat, and they put that tube into a bowl of something, some fluid. And what do you think that happens to the fluid that's in that bowl where the tube dips into? It's sucked up. Is there a pump to push it up? I mean, you probably don't even own and haven't even seen a carburetor in your life, right? Automobiles used to have carburetors. How did that work? Venturi effect. The necking down of the airflow, then it draws the little gasoline up through the needle area. What do they call that? For the gasoline flow. How many people have ever seen anybody with a garden hose and they have a little attachment on the end and the bowl on the bottom of that attachment, and they're going around and spraying their plants, either to kill the bugs that are eating the plants or something else. Maybe they're killing other plants with it, right? In a garden? How's that bowl mixed up with either a pesticide or herbicide concentrated in that bowl? How does that come out? Well, there's a little straw that goes in, and this Venturi effect has a lower pressure and draws it up, and it mixes and sprays out with the water, typically at a garden hose. You don't have to have water and a herbicide or pesticide to spray it, or gasoline in a carburetor to spray it or bring it up and mix it with the air. You can also have air, and you could have paint. You could have a little tube going down the liquid paint, and then that's drawn up, and so it's an air paint sprayer, and it runs off compressed air in the back, right? So you'll see that often, and it's explained with Bernoulli's equation, and you see why the pressure in that throat's much lower, and it can draw up other fluids. Let's talk about a pitot tube. This device is used to measure airflow in a channel or duct or something. And usually what you do is, if this is your duct, you stick it in, and this is grossly oversized. It's pencil thin, if not smaller. You line it up with the direction of flow so that the flow is coming at it this way. You can't have it cockeyed in the flow. It needs to be lined up. And it has an opening right here. I'll color code it blue right here. And there's air. If this is measuring air, there's air in this tube that goes down to the center until it hits a liquid layer, a liquid surface. Maybe that liquid's water, H2O, that's shown here. Water. Could be mercury, but in air systems it's often just water. And then on the outside, it has some other holes right here. You can kind of see them. There'll be a couple of them around the circumference of that tube, a little bit back from the tip, and that is connected in it with another passage. Let me change the color here so it's more obvious. Through another passage that comes down and comes over to the other side. And now some of these holes are connected that way, and they come like that. Okay? And so what's down in this vicinity? I have gas or air on one side and the blue, the purple on the other side. That device is known as a barometer. Manometer. You take your pick. Which one? Manometer or barometer? Manometer. That's right. Manometer. Okay, so now what does that manometer do? It tells you the difference in the pressure of those two sides. Which one in this illustration has a higher pressure? The blue or the purple? The blue. The blue is a higher pressure. So what you're saying is this the air right here at the tip of this pitot tube has higher pressure than the air on the sides of the pitot tube. Okay, what you do now is you back up and you apply Bernoulli's equation to little chunks of air. Some of them are starting out right here, and they just flow, and they're going to hit dead on to the tip of that pitot tube. And one unfortunate little pack of fluids going straight there, and when he hits it, he comes pretty much to rest before he turns the corner and gets around it. Okay? So the kinetic energy of that pack right in that vicinity goes to zero. I know it doesn't go perfectly to zero, but it goes essentially to zero, and then it slides around the side. Okay. So over here, we had the pressure, the flow energy, plus the kinetic energy in 1/2 rho v squared. That seems funny, Professor. The units on that are not energy, it's pressure. I can see it. It's pressure. I know it's pressure, but it's energy per unit volume. That's how you can interpret pressure in Bernoulli's equation. Okay, so this pressure right here, because the kinetic energy goes down, is the highest, isn't it? Isn't P2 at the stagnation point at the tip of the Pitot static tube higher than P1? It is. And so it's going to be P1 plus 1/2 rho v squared, whatever that velocity is back here as it approached it. That's that kinetic energy per unit volume plus the static pressure. Now, what happens if the chunk of fluid is over here or over here? Well, they're going to flow and flow and flow and flow, and guess what? They don't come to rest at the tip. And so their pressure and the kinetic energy always remains the same. So the kinetic energy of this pack of fluid stays the same as the kinetic energy of that all the way through the system, and the pressure is the same. So what you have is that the pressure on the side that's being measured over here is the static pressure of the fluid in the duct or in the pipe, whatever you're measuring.
Would the pressure change if the static tube was designed less right angles? Like would it was more rounded insides?
Yeah, there's a, on the tip right here, it's curved a little bit with the hole, and then curved a little bit like that. So what you do also is you come back a little ways, and you don't put the slots for the picking up the static pressure real close to the tip. You put it back a little ways, so that if there is a little flow separation, it gets reattached, such that these tubes are measuring the pressure that's the static pressure a little ways away. It's not influenced by some two-dimensional, three-dimensional flow right in the near vicinity of that curvature. And you wouldn't want to design it with a blunt edge, because with a blunt edge you would get more separation coming off that edge, and then it would have to be delayed longer down the tube before you had the good static pressure. That make sense? Okay. So you have the static pressure pickup on the sides, and in the front you have what they call the total pressure, made up of the static pressure plus the velocity pressure. So what's the difference that the manometer measures? The manometer measures the delta P of the manometer, which is the difference in the pressure between the tip and the sides. And the difference in the pressure in the tip and the sides is 1/2 rho v squared, which is the velocity pressure. Or some people will call this not the velocity pressure, the dynamic pressure. I prefer the velocity pressure because it's coming from the fluid having non-zero speed. But I think this book and a lot of books call it the dynamic pressure. Okay. And so what you can do is you can make a measurement of the density of the fluid in the manometer, G, because manometers work in a gravitational field, and the height difference in that fluid column in the manometer, and then you can use it to go and infer the speed of the fluid. You stick this in, you want to make a measurement. How fast is the fluid going? Got a manometer attached to the pitot tube, I look at it, and now I can infer the speed of the airflow. Let me ask you this question. Is that density right there the same as that density right there? No. One of them is like water in the manometer. One of them is air that you're measuring. Usually the pitot tubes are used in airflow. Okay. Density of air maybe is about 1.2 kilograms per meter cubed. Density of water around 1,000 kilograms per meter cubed. Big difference. Okay, so the equation would be the velocity of the air is equal to 2 times density of water divided by the density of air. The units will cancel, so I'll group those together. GH square root. Look good? That's how you would make a measurement. That's how they do make measurements of the pitot using the pitot static tube. Any other comments?
So why does the opening have to be small if I don't see anything in the equation for the area?
Oh, well, we do know that the probe now has really been an obstruction to the flow. And so if I look at it, maybe I'm having a square duct. I don't want to put a pitot static tube of this diameter in the square duct. It really needs to have a small cross-sectional area because it is blocking it. But it's blocking it as such a small fraction that I can use the approximation of Bernoulli's equation to get a correlation to predict the speed.
What about where you place it within the sampling?
What we'll do is ASHRAE and other organizations will say, how accurate do you want? And a lot of people say, I just want to get a ballpark. Well, they'll put it right in the middle, and they'll call that the average speed over the whole area. But they have all sorts of recommendations. They'll tell you what distance to put it and what pattern to put it to get the right, a better number for the average. Because this one in the middle will have a higher flow than this one near the corner. And if you had more of a oval shape, they have a pattern for that. If you have I've even seen some crazy shapes, some triangular. There's no triangular shaped ducts out there, but there's a lot of oval. There's a lot of oval as well as a lot of round ducts and a lot of rectangular ducts that are not necessarily square. They may be long and not so tall. So they have all sorts of patterns to where you should make the measurement, and they'll even tell you the weighting factor. Like this one, if you make, how many points did I put? 12 here? 12 points. This one may be weighted, I don't know, 1/24th, and this one may be weighted more. This may be weighted by 3/24ths or something. But the sum of all of them over all the points would sum up to unity. Okay? There's a lot of science in it, or engineering, that goes into it. But the pitot static tube is a very simple device, and it's still well used out there in practice. We're going to apply Bernoulli's equation more and more for flow in ducts and tubes and pipes. But one of the challenges is when you have a flow in a pipe, that's easiest to look at. You think about the center line of the pipe, and you know that the fluid flow is at rest at the edges, isn't it? But we want to use the equation, Bernoulli's equation, where we're saying the pressure plus 1/2 rho B squared plus rho GZ is equal to a constant for flow through a duct or tube or pipe. Well, what we find is we want to use our average speed right here. Well, there's a kinetic energy correction factor, alpha, which you'll see in some textbooks and in this textbook, to adjust for the fact that the net kinetic energy flow rate isn't equal to just 1/2 rho V average squared. If you put that kinetic energy correction factor alpha in there, it's a better approximation. Now, in a lot of cases, alpha is about 1. When you have laminar flow, alpha is farthest away from 1. And the textbook gives you and I'll derive this equation, the analytic expression for how to calculate alpha right here, this equation. If you want to calculate alpha, you do it by an area integral of u, the local speed, as a function of r, Think about R coming out like that. So I need U. I need to be able to describe U as a function of R and put it right in here. Divided by U average cubed, integrated over the area, then 1 over the area. How did they ever come up with this equation alpha? Let's do the quick derivation for it. So the goal is we want to have the kinetic energy flow rate, KE dot, the kinetic energy flow rate in the pipe approximated by the simple equation alpha times 1/2 rho V average squared. Well, how would I calculate the kinetic energy flow rate? I would sum it up over all of the little chunks of fluid that are flowing down that duct or pipe or tube. So that summation will be done by an integration. This is looking down, and I'll do the same thing that we did before, where this is a little string of area. And everything crossing that little ring has the same speed, hence it has the same specific kinetic energy. True? So what I do is I integrate over little rings of area that have the same speed and the same specific kinetic energy flow rate. Okay. So how would I do that? I say that 1/2 rho V squared is my what is 1/2 V squared? Is that a specific kinetic energy? Is that true? Specific kinetic energy per unit mass. If I have rho A, which is counted for the dA right there, and then V, then that is my little mass flow rate, little dm dot. And this is the kinetic energy per unit mass. And so that is a good integral for calculating the total flow rate of kinetic energy with the fluid. Does that make sense? Yeah? Okay. I need to back up here. I need to do the same thing on that side. What's 1/2 V average squared? The kinetic energy per unit mass. I need to multiply by the mass flow rate for the entire pipe, which is rho average times area. Okay, so that's the kinetic energy flow rate. This is my m dot, and this is my kinetic energy per unit mass. All right, so here's my equation, 1/2 rho V cubed dA. Can I cancel the 1/2s? If its density is uniform, and so we pick up the equation for alpha. Alpha is 1 over the area times the integral. We get a V cubed from there, and we get a V average cubed from there, from this side, bringing it over, dA. And there you go. That's the equation. The derivation of that equation is just like the derivation of, what was the equation for V average? Was it 1 over A integral of V dA? Just like that. All right. Again, the book introduces this kinetic energy correction factor. You'll see it in the Bernoulli equation when you apply it to flow in ducts, pipes, tubes. But often, I'll drop it out because alpha often is close to 1. When is it not close to 1? For laminar flow. When is it closer to 1? Turbulent flow. Siphoning. There's another application problem. So think about a tank filled with some fluid. And we want to move some of that fluid out of that tank and fill, I don't know, a bucket or a pail or a container with the fluid. We want to transfer that fluid. Maybe I show it having a little bit of fluid in it at the beginning. One way you could do it is have a tube like that. Okay? It's like a garden hose or just a little plastic tube. It's open and it's constant cross-sectional area. It's not expanding the diameter or anything, but there's the tube. It's of some length. Okay. And so if you can get the flow started in this tube, the flow will continue to go through the tube. How many people have ever done siphoning by themselves? Okay. How many people have seen it? How many people never did any siphoning? Never? Okay. That's interesting. Some other people. So we can apply Bernoulli's equation to study siphoning. Let's start and draw a streamline that goes like this. It's inside the tube. It comes down. And then we're going to stop it right at the exit of the tube. We'll go ahead and label state 1. We'll put state 2 at the inlet to the tube. We'll put state 3 at the highest elevation of the tube. It will put state 4 at the same elevation as state 2, just for reference and discussion purposes. And then we'll put state 5 at the outlet of the tube. Okay? Somebody says, I want to introduce a coordinate system. You can introduce a coordinate system starting with z at 0 where 5 is and measuring up. And so 5, z sub 5 would be 0. Z sub 2 equal to z sub 4, some elevation. And then z sub 1, and then the highest would be z3. True? Those would be our elevations. So without gravity, would a siphon hose work? No. It's going to be using gravity. So let's go ahead and apply Bernoulli's equation through this. And so we'll have the pressure at 1 plus 1/2 rho V1 squared plus rho G Z1 is equal to a constant anywhere. So is that constant equal to the pressure at 2 plus 1/2 rho V2 squared plus rho G Z2? Sure, if I just wanted to go from 1 to 2, but it's also equal to the same for 3, the same for 4, the same for 5. So P5 plus 1/2 rho V5 squared plus rho G Z5. True? Did I write Bernoulli's equation correct for that? Let's focus then on going from state 1 to state 5. So P1 plus 1/2 rho V1 squared plus rho G Z1. Which terms can we cancel out of the Bernoulli's equation going from 1 to 5? P1 and P5, they're both equal to 0 gauge pressure. They're both the atmospheric pressure. V1, 1/2 rho V1 squared, because the tank is large and I don't have a very fast drop in the level of that tank. So it's approximately 0. Z5, because we set the reference to 0. And so this equation shows us that the speed at which it comes out of the hose is related to 2G Z1 square root. True? That equation looks very similar to another equation we developed last time. 2GH, right. So we called that Torricelli's equation. So it's as if you had a tank which was like this. I'm going to just sketch it here. The tank comes down, goes across, and goes up, and the fluid level is all the way in. Forget the siphon, it's just now a super large tank, and the fluid comes out the hole at 5 with the speed given by Torricelli's equation. True? But we get rid of that, Now, we know that there is not going to be a perfect frictionless fluid that's going to be siphoned. So this will give us a prediction of the maximum outlet flow rate. It'll be less, won't it? V5 will be less than this, but this would give us an estimate of the outlet flow rate. Okay. If I wanted to get the volumetric flow rate going through it, would I just multiply by pi d squared over 4 times this V5? Yeah. Okay. The diameter of the tube is constant. We mentioned that. Let me ask this question. The velocity of the fluid in the tube at state 4 compared to the velocity of the tube at state 5. Is the velocity of the fluid in the tube at state 4, is that greater than, equal to, or less than the velocity at the exit state 5? Answer A, B, or C. So compare the velocities. It's at state 4 and at state 5. Just, yeah, the diameter is constant. And so it's answer A, B, or C. The velocity at state 4 compared to the velocity at state 5. All right. Let's go ahead and show the results. One of the things that's challenging when you solve problems like this is Bernoulli's equation, is that you're jumping back and forth between mass balance and energy balance. Okay, so some people got this answer correct. And the answer that to get the right answer is B, would use what concept? You had asked the question. When I asked the question, you asked me, you said, hey, is the diameter constant? And we just went over that. The diameter of the tube is not changing. The diameter of the siphon is not changing. So it's rho AV is the mass flow rate. The mass flow rate passing through each section of the tube from section 2 to section 3 to section 4 to section 5 is all the same, true? So the mass flow rate at 4 is rho AV at 5. It's not, the liquid's not changing density. The area isn't changing. The speed has to be the same.
So since we have to consider the gravity as an acceleration,
right,
we can definitely tell that the gravity is acting from 4 to 5. So how can that be equal?
Okay, I'll answer that in a minute, but this is the leading to where I'm going to go.
If you were to extend that to larger proportions, would it still be accurate? Like 100 feet, 200 feet?
No, you can't do that. And I'll talk about that as well. There's only a certain elevation that 3 can go to.
For the velocity to be equal, correct?
Before something bad happens, which is like cavitation.
Okay.
And so that's, yeah, I'm going in that direction too. Somebody else had a question?
Doesn't velocity depend on the height as well?
Yes. And so from this, let me get rid of this. So from the exit speed 5, if I have Z1 higher, if I raise the tank, the amount of fluid flow coming out of that siphon will be higher. It's proportional to the square root of the elevation difference. Right? So that one I can answer. The other two I'm answering right now. To answer your question and your question, I need to consider pressure. So the next question is look at the pressure at 4 versus the pressure at 5. Is the pressure at 4 greater, equal to, or less than the pressure at 5? Answer A, B, or C. Just focus on pressure. Is the pressure at 4 greater than the pressure at 5, equal to the pressure at 5, or less than the pressure at 5? All right. Now, when you think about pressure, I need to not do it by mass balance. That was how I answered the question on velocity, but I need to really think about energy. And so I would use Bernoulli's equation just between 4 and 5, and I'd write down that the pressure at 4 plus 1/2 rho V4 squared plus rho G Z4 is equal to the pressure at 5 plus 1/2 rho V5 squared plus rho G Z5. Now, the rho G Z5, we set the reference to 0. We said that the speeds are the same, so the kinetic energy contribution is the same. They cancel. And we see that P5 is equal to P4 plus something, rho G height difference. The elevation at 4 is higher than at 5. So from this equation, you would see that 5 is greater than 4. So the pressure at 5 minus the pressure at 4 is a positive rho G Z4. All right? So the pressure at 5 is greater than the pressure at 4. So that's correct. True? Did that make sense? Okay. Let me ask you this question. What does it look like the pressure at 5 is? I already mentioned at the beginning. Is it near atmospheric pressure, below atmospheric pressure, above atmospheric pressure, pressure at 5? It's right at atmospheric pressure. Okay. And we just concluded that the pressure at 4 is below pressure at 5. Describe the pressure at 4. It's a state of vacuum. It's a slight vacuum. So if a little mischievous person came and drilled a hole in 4, okay, popped the hole in 4, I'd like to ask the question, does the air on the outside of the tube rush in? Or does the water or the gasoline or whatever you're siphoning, the fluid, the liquid on the inside of the tube, squirt out of the hole? Air is going to go in. Air will go in. It'll break that siphon.
Okay, so Dr. Machado, a few weeks ago you said that P1 is less than P2, right? And we can say that P2 equals P4.
Okay, you're getting ahead of me. I need to get there, but let me build to it because just let me get there. Okay. Now, if you have a very super long siphon, okay, a couple things you might want to consider. How strong are the walls? What could happen? The walls could collapse because of the pressure on the outside and it's under a vacuum essentially on the inside. I didn't say a strong vacuum, I just said it was under below atmospheric pressure, true? So it could, if you had real weak, it could pinch it back or suck it in and kink it some way. But if you go and extend this also to, let's say, move to a higher elevation, let's say move to 0.3, well, what happens if 4 goes up and up and up? Well, Z4 goes to Z3, you're going to get a greater pressure difference. It could get to where the pressure at 4 is at the saturation pressure of that fluid. Then the fluid wants to not stay liquid, it wants to go into vapor. Okay? And so you can't have super long these siphons. I think I gave you the answer to the next question I wanted to ask is, how about where is the lowest pressure anywhere in the system? Is it at 1, 2, 3, 4, or 5? The lowest pressure. Four or 3 or 2? It's at 3, right? Isn't it at 3? Okay, I need to do this. I need to clean and get some more here. Let me do this. I'm going to stop and save this. All right, here's another question. Let's apply Bernoulli's from state 2, the inlet to the tube, to state 4. Why did I pick them? Because they have the same elevation. Okay? So if we look at 2 and 4, can you tell what is the pressure in the tube at 2 compared to the pressure in the siphon at 4? Is it the same? Is it greater? Is it less? What is the pressure in the tube at 2 compared to the tube at 4? Should we vote on it? Let's go A, B, C. So what we would do to answer that question is write Bernoulli's equation down. We'd say the same kinetic energy because it has the same speed. And it has the same elevation. Hence, B. Isn't B the correct answer? They're the same pressure. Now, this always throws students for a loop. Other times what I'll do is I'll ask the question, don't go from 5 to 4 first. Go from 1 to 2 first. And I'll ask the question, I'll say, the pressure at 1 compared to the pressure at 2, is it greater, equal, or less? Answer A, B, or C. Let's just see what we got. The pressure at 1 versus the pressure at 2. This is challenging, isn't it? It's challenging. So a lot of people, they forget about fluid flow. They just came out of fluid statics. They say, hey, you got a tank. I see this pressure. It's going down. Hey, pressure at 2 is higher. Pressure at 2 has to be higher. That's what they'll say. But things are moving. Things are happening from 1 to 2. Talk about the kinetic energy at 1. Negligible. What about the kinetic energy of a little pack of fluid at 2? It's whipping along. It's going, right? So what we had was we had the pressure at 1, which is some energy per unit volume, plus the kinetic energy at 1, 1/2 rho V1 squared, plus rho G Z1 equal to the pressure at 2 plus 1/2 rho V2 squared plus rho. You get tired of watching me write this? I get tired of writing it. All right, so we're going to compare 1 and 2. This is negligible. True. And what do we have? We're going to have that the pressure at 1 minus the pressure at 2 is equal to, put it like this, plus rho G Z1 minus Z2 equal to 1/2 rho V2 squared. All right. What is this right in here? What is this? This is positive. What's rho G Z1 minus Z2? Positive. That really doesn't help that much, does it? But what do I do here? I already deduced that the pressure at 2 is the same as the pressure at 4, wasn't it? And we already deduced that the pressure at 4 is less than the pressure at 5. True?
Sure. Pressure at 1 and 5 equal.
Pressure at 1 and 5 are equal. So what do we get? That the pressure at 2 is less than the pressure at 1, even though the hydrostatic pressure is trying to build it up. Oops, I hit the wrong thing. I got to stop that. Stop. I got to hit this thing. And then I go back to grade that C, question 7, right? Pressure at 2 is less than the pressure at 1. Even
I'll be fun with that.
pressure at 2, yeah. The 68% were saying, yeah, go. Sorry about that. It's a lot harder to see it from going from 1 to 2 only by itself.
Well, the truth is we're still stuck with studying fluids. So
You're fresh off of studying statics, and so you're thinking statics. Anytime you go down in a fluid, but this is you're going down, and the fluid is not stationary along that streamline. It went from zero kinetic energy to a significant kinetic energy at state 2, and that's the difference. It accelerated. Okay. Yeah, it accelerated. All right. Okay. So I think I already mentioned this. To get, once you have the speed at 5, which is the same speed at 4, same speed at 3, same speed at 2, then you multiply it by the area, and you get the density in the area, you get the mass flow rate. How do I increase the mass flow rate of the siphon? I can either increase the area, or I can increase the speed by increasing the elevation difference. True? I can increase, if I wanted to, I increase Z1. Okay. Does Z3 have an effect on the speed through the through the siphon? No. Here's another one. Does Z2 influence it? Somebody says, don't put that tube that low in the container. Put the tube so it's right near the top. Or no. Put the tube so it's right near the bottom. Will Z2 influence the flow rate through the siphon? As long as you don't get it where it comes out. If you get it out, it breaks the siphon, it won't work. Or if you get it too close to the bottom, it could be, blocking the flow into it because it sits on the bottom and sucks on the bottom. It'll actually pull itself down and stop the siphon on the bottom. But no, the elevation doesn't matter. You can change the elevation in the tube a little bit. It won't change the flow. If I change the 5, the location of 5, maybe I move it down further, will that change the flow rate? If I change the location of 5? Well, yeah, maybe I should have put 0 way down here. And then in all the equations, it would be Z1 minus Z5. It's always the difference between the fluid level in the tank and the outlet of the tube. Okay? All right. I'll do one more application problem. I just thought of it, so bear with me. Let's have a tank like this. And I just want to fill up a container down here. Maybe I should draw it the same container with the fluid. And maybe the container, make it small diameter. Here's a container. Okay? And I want to fill it up from empty to this level in the shortest amount of time possible. Somebody says, take the container just like that. That's great. And if you increase the height of the fluid level in the container, it will fill up the container faster. Do you agree? Yeah, it'll agree. Somebody comes in and says, you have an option. You can have a little opening like this, or you can have a little opening with a little pipe that comes down. So which one is going to fill the container faster? The opening only that little opening, or the opening with the little tube coming down some distance with this little tube? Which one will fill it faster, or will they not? Will they fill it at the same rate? Okay, I know that I'm asking this on the fly, so only the opening, or with tube, or they'll be the same. Which one will fill faster? Without the tube? Will that fill the fastest? With the tube? Or, hey, they're going to fill at the same flow rate because you're not changing the elevation or anything like that. Last clicker question, I promise. All right. Well, how would I answer that question? I've said it 10, 20 times. How would you answer this question? Apply Bernoulli's equation from one point to another point. True? And so I would do it for here. I would pick a point. Maybe this is point 1, and I'd go to point 2. Or I go from 1 to 3. Right? In case 2, what is the pressure at 2 if there's no tube? What is the pressure at 2 if there's no tube?
Equal.
Atmospheric pressure. It's equal to P1. What happens if I have the tube? What's the pressure at 3 compared to the pressure at 1? They're equal. Okay. So if I have the tube, what happens to the pressure at 2? With the tube? Does it stay equal to atmosphere? It drops. Isn't it lower with the tube? And so now, I think knowing that, you know it's going to have a greater draw through the whole thing. You'll have a greater flow rate with the tube. True? So the flow rate with the tube will be greater. Okay? You can do this too. Just compare and do 1 to 2 with Bernoulli's. P1 plus 1/2 rho V1 squared plus rho G Z1 equal to P2 plus 1/2 rho V2 squared plus rho G Z2. Okay, we're going to say that the kinetic energy at the surface is negligible. And the pressure at 1 and the pressure at 2, because it's no tube is there, it's just open, are the same. And so the exit speed is 2 rho G H, which is Z1 minus Z2 square root. That looks like Torricelli's equation. We do the same thing, but go from 1 to 3. You find V3 is equal to square root 2 rho G Z1 minus Z3. This is a greater speed if you have the tube, with tube. All right, let's grade it. Be done. What? Come on now. So it's B. No more clicker questions. Right. We have time for moving into this problem. What I'd like to do is I'd like you to solve this problem. And I'll take a pause and walk around and see how far you go. So what do we have? We have a sealed water tank is filled up to 12 meters of water and air at 150 kilopascal gauge pressures on top. So here is the water level. Above it is air. And the water level in the tank's 12 meters. The tank is connected with a hose that goes to a nozzle. So this is our hose. And it shoots the water straight up into the air. So the water can go up. And it asks, what is the maximum height that the water could reach? What is this maximum height? Okay? So I'm going to go ahead and stop and let you work on that for a minute, and I'll walk around and give you assistance. All right, so I would start by putting a node and apply Bernoulli's equation along a streamline, and I draw that streamline going where the fluid goes and end it right here. And so that would be 1. I could introduce other locations, let's say 2 and 3, and then I could study it to death, and 4, but there you go, 1, 2, and 3, and 4. But let's just say the pressure at 1 plus 1/2 rho V1 squared plus rho G Z1 is equal to the pressure at 4 plus 1/2 rho V4 squared plus rho G Z4. Did I apply Bernoulli's along that streamline? I know there's some assumptions. It's inviscid. Good luck. Right? But this is a maximum height. When I account for some viscous effects, it'll reduce that maximum height. The actual height will be less. But what about this pressure at 1? Well, it's 150 kilopascal. What about the pressure at 4? It's 0 kilopascal. Okay, well, somebody says, I would prefer to work in absolute pressure. Great. Then this is 250 kilopascal absolute, and this is 100 kilopascal absolute. I approximate that the atmospheric pressure is about 100 kilopascal, okay? But you don't have to do that. You can work all in gauge, so I would just leave it all in gauge. Now, what about the kinetic energy at 1? Essentially 0 because it's a large diameter tank. No information is given on the diameter. And then, what do we know? We know that the measurement of this water level going up is 12 meters from the bottom of the tank. Then that is conveniently the same as the exit of the nozzle. H is measured upward from the same location. So Z4 is H. And Z1 is 12 meters. 12 meters. True? Okay. So the other thing is, this is the maximum height. It's like the maximum height that a ball gets thrown in dynamics, right? What about the velocity at 4 when it's at 0? Okay, it doesn't mean the velocity at 3 is 0. No. It means the velocity at 4 is 0. Okay, I think we're ready to then say height is going to be the pressure at 1 plus rho g z1 divided by rho g. Or pressure at 1 divided by rho g plus z1. Okay, so we have 100 kilopascal. And then rho g for water. Well, that's 1,000 times 9.81. 9.81 kilonewtons per cubic meter. And Pascal, Newton per meter squared. And so that should work out where I get the Pascal, the Newton, the kilo, and then I'll have only a meter left in that unit for P over rho G. And then I'll add to it the 12 meters. So the height, the maximum height, comes in at 12 plus 15.3. So it's 27.3 meters. Oh, I wrote that down wrong. But if you run it 150, thank you for the correction. You'll get the numbers. Did that help? I'm not going to do any more clicker questions for today. Maybe I'll just pick on somebody and say, you tell me, what about the pressure at 2? What do you think the pressure at 2 is compared to the pressure at 1? Yeah, it's going to be difficult, but yeah. Okay? Okay. Let's move on. Somebody says, yeah, you had an air pressure tank up here, or air pressure above the surface, and it supplied 150 kilopascal. What would be the difference in the height that the water would shoot if I cut and put a pump in to my system? See how I put the pump in? And I run the pump such that if I take and measure the pressure on the inlet to the pump and compare it to the pressure on the outlet to the pump, the pressure on the outlet of the pump is 150 kilopascal greater than the inlet. And I cut open this tank such that it's atmospheric pressure on the top. What do you think? Do you think that will give us a difference in the height? It will not. You'll get the same maximum height. Now, what you can do when we first are introduced to this notion of, hey, you're changing, you can't really apply Bernoullis across that pump. I know. So what you would do is you would say Bernoulli from 1 down to 2. And then Bernoulli from 2 or 3 out to 4, like that. Okay? And then you would patch them together and say the pump elevates the pressure to go from 2 to 3. So pressure at 3 is equal to the pressure at 2 plus the pressure gain across the pump of 150 kilopascal. Should I work through that math, or is it clear enough that you could do Bernoulli from 1 to 2, use this for information about the pump, and then do Bernoulli from 3 to 4, and you would calculate the same maximum? That seem reasonable? Yeah? Yeah. Well, what you can do is you can just modify Bernoulli's equation. What is it's a mechanical energy equation, and it can be written as mechanical energy per unit volume, per unit mass, or per unit weight. True? A lot of times we put it in energy per unit volume, which has pressure. So if it's an energy per unit volume, think about this. I start at state 1, and I'm not going to stop at 2 and go to, I'm going to just kind of go all the way through to the final state 2. And I'll say it's this energy, the flow energy at 1 plus the kinetic energy at 1 plus the potential energy at 1. That's like what I start off with, plus any gains equal to the pressure at the end plus the kinetic energy at the end plus the rho, I can't speak and do this at the same time, rho gz, the potential energy at the end plus any potential losses, because I could now account, if I can account for gains due to something like pumps, I could count for losses due to maybe some modification for frictional losses. Only one other thing we could put in here to really make it look fancy, alpha. What is that alpha? Kinetic energy correction factor, which normally is 1. Close enough to 1, we ignore it. And this could be the alpha at 1 and the alpha at 2 if you wanted to really get sophisticated. So now we have what I call modified Bernoulli's equation. It's a statement of the conservation of mechanical energy, but it includes some mechanical energy gains as well as some mechanical energy losses. Here it is. So you can have it for, in the terms of pressure, energy per unit volume. Notice we put the alpha there. Here's a pressure gain or a delta P gain. It's a pressure gain due to something. And if you had a pressure loss, you could include it on that side as well. You could also express it not as a pressure gain, but an energy per unit mass gain, or a head gain, or a pressure loss, or energy per unit mass loss, or a head loss. And so now we've modified these to account for gains and losses. Looking back at this problem, where do you think there might be some losses in the real system to make it a little more accurate so that we don't just have the maximum height? We'll never get the maximum because there's really some friction and other losses in the system. Where would we look? Probably right in here on this inlet. Probably along the length of a small diameter tube or pipe or fitting or something. Probably right in maybe somewhere like that nozzle. Okay? If we have a bend or a 90-degree elbow, that's where we would have some adjustments for actual losses to be closer to the real system. Oh, I'm out of time. Thank you very much for your attention.